Hi everyone, my name's Nathan and I'm a postgraduate research student at Keele University in the UK. Today I'm going to be talking you through a paper that I collaborated on with my colleagues, Dr Simon Powers from Edinburgh Napier University, which is also in the UK, and Dr James Borg, who works with me at Keele University. The paper's titled A Mechanism to Promote Social Behaviour in Household Load Balancing, and I hope you enjoy. As I'm sure you're all aware, climate change is one of the major problems facing the world today. In the UK, where I'm from, there's a legal target to reduce greenhouse gases by 80% by 2050, and many similar legal targets exist across the world. A key part of meeting these targets is moving towards using renewable sources of energy. However, integrating renewable energy sources into national grids, like we have here in the UK, or other large-scale systems can be challenging. A major difficulty comes from the fact that the output of renewable energy sources is often dependent on weather conditions. While a fossil fuel-based power plant may be able to be powered on when there's a spike in demand, if you're reliant on wind turbines, for example, it's not possible to simply turn on the wind so that you can account for a spike in demand. This key problem of load balancing, which is making sure there's enough power to meet demand, is therefore particularly important when using renewable energy sources. Governments and energy providers across the world have recognised that this problem of load balancing is easier to solve on a local scale. One way to reduce the scale of energy distribution is to develop community energy systems in the form of microgrids. In a microgrid, the users of the system have joint ownership of some renewable energy sources, such as solar panels or a wind turbine. The users of the system manage the distribution of generated energy and have the option to buy additional energy or sell excess energy to other connected microgrids or a larger power grid. Simply put, in community energy systems, users take over managing the load balancing that's traditionally handled by a larger national or international grid. As you cannot simply turn on a renewable energy resource, users need to flatten the energy usage curve. As the graph on the right shows, power usage within a household fluctuates greatly. The idea of flattening the curve is very similar to the discussions of flattening the curve regarding the ongoing COVID-19 pandemic. When taking all users of a community energy system into account, it's important to flatten the overall usage curve as much as possible so that the renewable energy sources can handle the demand. If this curve is not flattened, then potentially non-renewable energy would need to be bought in from outside of the microgrid, or large sums of money may need to be invested in potentially inefficient energy storage methods. The traditional solution to flattening the energy usage curve is differential pricing, such as Economy 7 tariffs in the UK, which allow cheaper energy for 7 hours at night when there's less national demand. This method, however, discriminates against low-income households, relegating them to using less convenient time slots. In a community energy system, this approach has an additional concern: who would set the pricing in a user-managed system? Ultimately, users of a community energy system need to spread out their usage and may need to use high-powered appliances at times other than when they prefer. Rather than differential pricing, one promising consideration is a decentralised approach. In a decentralised approach, households, which could be represented by software agents, possibly integrated into smart meters, negotiate when to use their high-powered appliances. Many modern smart appliances, such as washing machines and dishwashers, can be time delayed, and so by negotiating with one another, users could spread their usage out over the course of a day, helping to flatten the energy usage curve. When developing a new approach to load balancing, users need to perceive procedural justice, meaning that the processes by which decisions are made are seen as fair and are transparent to the users of the system. Users also need to perceive distributive justice, meaning that the results of the system, in this case the distribution of renewable energy, are seen as fair. Our hypothesis is that households will perceive this decentralised approach as fairer when compared to a centralised allocation mechanism. We started by looking at a model developed by Petrucci, which is based around the idea of individuals being allocated time slots of when they can use their high-powered appliances. Within the model, a hypothetical community energy system exists, with 96 individual agents representing different households with varying preferences for when they want to use their high-powered appliances. Each day, these agents request 4 out of a possible 24-hour-long time slots for simplicity, all requests were for the same amount of energy. To model the capacity of the system, no more than 16 agents can use the same time slot on any given day. This system has a clear optimization problem. The system needs to satisfy as many preferences for time slots as possible across all the agents. An agent's individual satisfaction is represented between a 0 and 1, and it's determined by the number of time slots that they have requested being allocated to them. So that if 3 of an agent's 4 requested time slots were allocated to them, they'd have an individual satisfaction of 0.75. There's also a social problem with this system. The time slots need to be allocated such that households perceive the system as fair and in a way that respects their privacy. To address the optimization and social problems, a decentralised allocation mechanism was developed. Initially, all available time slots are allocated to households at random. Each agent representing a household can then request to swap one of its allocated time slots with another agent up to a set number of rounds of pairwise exchanges per day. For each request, the agent receiving the request decides whether or not to fulfill it. There are 2 types of agents that exist in the system: selfish agents and social agents. So, selfish agents only accept an exchange that gives them one of their preferred time slots. Social agents will also agree to these mutually beneficial exchanges, but additionally will make decisions based on social capital. In this model, social capital is represented by favours. Social agents additionally accept an exchange that has no effect on their individual satisfaction if they owe the requesting agent a favour. The favour means that the requesting agent has given the receiving agent a time slot that the receiving agent requested on a previous day. This model was found to encourage social behaviour, with cooperating agents negotiating their way to flattening their collective energy usage curve. The model developed allows for an easily understandable system, promoting procedural justice, while high levels of average satisfaction promote distributive justice. However, we were left with many questions about the approach and how it could be applied to a real-world scenario. We chose 2 of these questions to try and answer in this paper. First, we asked, to what extent is tracking social capital necessary to produce socially beneficial outcomes? What would happen if social agents simply accepted all incoming requests that didn't have a detrimental effect on their own satisfaction? Secondly, we asked if agents can learn to adopt the selfish or social strategy by observing the strategies of other agents in the system, will self-interested agents learn to behave socially? To answer our first question, in our redeveloped model, we allow social capital to be turned off, such that agents always accept exchanges that do not negatively affect their own individual satisfaction, rather than only when they owe the requesting agent a favour. To answer our second question, we implemented daily payoff-biased social learning. For our social learning, we first picked 2 agents. If the satisfaction of agent 2 is greater than the satisfaction of agent 1, agent 1 may switch to the strategy of agent 2, with the probability of switching proportional to the difference in their individual satisfaction levels for the day. To observe how this learning affected the results of the system, we reran our simulation with a varying number of agents that can learn at the end of each day. We did this such that with a 50% learning rate, 50% of the agents would be randomly selected to be agent 1, and observe another agent, potentially choosing to adopt their strategy after each day within the simulation. With a 100% learning rate, all agents would observe another agent and thus potentially change their strategy each day. So these first results show baseline results from our simulation. Here we started the simulation with 100% of the agents having the same strategy, either all being selfish or all being social. There were therefore no interactions between agents of different types, and so we were able to find the base performance of each agent type. As you can see with the leftmost graph, while selfish agents performed better when more exchanges took place, after as many as 200 rounds of exchanges, they were only able to reach an average satisfaction level of roughly 0.75 out of 1, or 75%. Social agents, on the other hand, were able to reach an average satisfaction of 91%, whether or not social capital existed within the system. However, when social capital existed within the system, social agents did require the simulation to run for a number of days before they reached their maximum potential, so that they could build up a history of favours between one another. Running a separate, centralised algorithm showed us that an average of 91% satisfaction was approximately the optimum performance this system could achieve. Reaching an average satisfaction of 91% is therefore an excellent result for the social agents. We next ran the simulation with a mixed population of 50% selfish agents and 50% social agents. We ran the simulation without social capital being taken into account, with social agents simply accepting any requests that were not detrimental to their own individual satisfaction levels. We found that while the system did not perform too poorly, we were not able to see the optimum performance achieved by an entirely social population. Most importantly, as shown in the third row of graphs, without social capital, the population as a whole did not fully adopt the social strategy which we know can achieve optimum results. When we turned social capital back on, the results were much closer to what we expected. As the simulation ran for more days and more rounds of exchanges took place, social agents were able to build up a history of favours given and received between one another. This allowed social agents to improve the satisfaction of others while building up social capital in return. In this scenario, the third row of graphs tells us that the social strategy was able to become dominant within the population and eventually lead to the wholly social population that allows for the agents to reach the optimum 91% satisfaction rating. Social capital is clearly essential in promoting the social behaviour which can optimize the performance of the system as a whole without requiring a centralised algorithm. These final graphs compare the average satisfaction of all the agents within the system between when the system allowed social capital and when it did not allow social capital. The purple boxes show us that when looking purely at system performance, by not implementing social capital, we are able to see improved performance early in the simulation. However, the orange boxes show us that when social capital is included, there's improved performance later in the simulation. This is because over time, the social agents are able to dominate the population and optimize the system's performance. To answer our research questions, we first asked to what extent is tracking social capital necessary to produce socially beneficial outcomes. The fact that the social capital is represented as favours ensures that it's easy to understand. Repaying a favour is a simple concept, and having this at the core of how the system operates facilitates procedural justice. The main reason that social capital is necessary in producing beneficial outcomes to a large extent is that as social capital is key in optimizing the system's performance, social capital is crucial in facilitating distributive justice. More users of the system will find it to perform fairly if they are more satisfied with their individual results. We also asked if agents can learn to adopt this selfish or social strategy by observing the strategies of other agents in the system. Will self-interested agents learn to behave socially? We found that self-interested agents will learn to behave socially with a mechanism that tracks social capital, in this case favours given and received, but not without social capital. As an additional point, the social strategy implies flexibility on the parts of the agents, which would be even more useful in harder optimization problems. I hope you found this presentation interesting, and I will now answer any questions. If I don't get around to answering your question, or you think of a question at a later date, feel free to email me at n.a.brooks@keele.ac.uk and I'll answer as soon as possible. So, any questions?